Thank you to the organizer for putting together this workshop. It was really a wonderful workshop. I would say the first Zoom workshop that I really like in the post-COVID era. So thank you for having me here. So today I will tell you a little bit about the merger proper phase, so the phase of the evolution of two neutron stars where they're actually colliding. And I want to emphasize some of the consequences of the merger dynamics and how this merger dynamics is imprinted in the electromagnetic signal. I want to emphasize that it's important to look at this because the merger phase is perhaps one of the last phases of the evolution that we understand relatively well before we go into the messy post-merger dynamics. So if I manage to change slides, so I prepared a visualization of the merger phase of two neutron stars. So what you see here is the density in grams per cubic centimeters. I've cut everything above the orbital plane. And what you're seeing here are two neutron stars that are about to merge. You can see a little bit of the tidal tail of the stars coming out. There is not much tidal tail here because it's an equal mass system. But pay attention to what happens in this couple of milliseconds as the stars touch. So here they are merging. There is a little bit of eject as the stars are merging. The tidal tail is expanding. And then after about one revolution of the binary, after the contact, there's this big splash of material coming out. This is density. I want to show the same thing. Now I'm showing the electron fraction of the material. This is this very same simulation, but now I'm color coding the electron fraction. Here blue is high, very neutron rich material, and red is less neutron rich material. You can see again the tidal tail forming, the stars bouncing together, and then there is a bounce back of the binary, and then this big splash of material coming out. And at late times, you see a neutrino-driven wind coming out of the remnant. So what I want to emphasize here is that despite some confusion on this in the literature, actually the vast majority of dynamical eject is not produced by the collision itself between the two stars, but at the time when the remnant bounces back. And you can see this a little bit more quantitatively if you look at this diagram. That's maybe less pretty, but actually easier to read, at least for me. So what I'm showing here is the central density of the two stars. This is the very same simulation we have been looking at. And what you see here is the outflow rate. The outflow rate is measured at some distance from the binary. So here I have done my best to shift the curves in time according to the velocity of the jet. What you can see here, this is the inspiral. The stars are orbiting each other. There is a little bit of a dip. This is the time of merger. So when the gravitational wave amplitude reaches a maximum. Here the density goes a little bit down because the stars are a little bit decompressing as they fall towards each other. Here they crash into each other, the density goes up. And then there is a centrifugal bounce of the remnant. And when the remnant expands, this is the phase where this remnant bounces back into the debris cloud. It launches a shockwave, and most of the eject that you can see here, the mass outflow rate starts to come out at this time. This purple curve is the fast tail of the ejector, so just the part of the ejector that's traveling with velocity larger than 0.6 c. So this is a somewhat arbitrary cutoff. You can see that this fast tail has two components. For this binary, there is a component really driven by the collisional shock, but it's very small, and actually most binaries do not show this component. This is an exceptional binary that also has this component, but most of this fast outflow is really the very tip of this shock. It's accelerated at the very tip of the shock that expands out of the bounce of the remnant. So here the main message I want to emphasize, because this has been discussed to some extent within the meeting, but not too much, is that when we are looking at dynamical ejective, we're really probing whether or not the remnant bounced back. So we can say something about whether there was a bounce or whether there was prompt black hole formation. So this is a very powerful probe for the equation of state. There is an issue with the mass ratio, but I will come back to that in a minute. The other thing I want to emphasize, and here I apologize, this plot is a bit busy, is that merger dynamics is also what drives the formation of the accretion disk around the remnant, which will then in turn power the bulk of the outflow. Actually, most of the outflow will come from the evolution of this disk. So forget for a moment about these dotted and dashed lines that represent unequal mass binaries. We'll come back to those in a minute. Focus for a moment on these binaries that have equal mass. These are three different binaries, same mass ratio 1. These have the chirp mass of 17/17, different equation of state, so different collapse time. So what we find is that the accretion disk mass grows with time, because actually the accretion disk at early time is not an accretion disk, it's more like an excretion disk. It's made of material that is squished out from the interface between the stars, so the two cores are merging together. So with time, there is actually material ejected out of the remnant into the disk. So the longer the remnant survives, the more massy the disk is, and then when there is black hole formation, a big chunk of the disk is immediately accreted, as you can see in this case here and in this case here. So if we know something about accretion disk mass, and we know something indirectly, because from the kilonova, we can infer how much material was ejected with large uncertainties that we had discussed. And from there, in principle, we can back up the disk mass. If we know how these systems evolve, we can say something about the lifetime of the remnant. So the lifetime of the remnant is directly imprinted in the electromagnetic counterparts, at the very least for equal mass binaries. Although this mapping may be difficult to figure out in practice, we can say something robustly. So we can say, for example, if there was a kilonova observed, then a case like this in which there is very little eject and all of the accretion disk is accreted into the black hole, these cases here are already ruled out. Now, what happens if we have large mass asymmetries? So for mass ratios larger than about 1.3 or 1.4, then the dynamics changes drastically, because at that point, you start to be dominated by the tidal ejection of dynamical material, and also the disk mass is dominated by tides, so by the tidal disruption of the stars. But this really happens in GR only for mass ratios about 1.5 or so. For these binaries, we can have very bright counterparts, even if the black hole formation occurs immediately at merger. So summarizing, if we know something about the mass ratio, then the very fact that we see or not an electromagnetic counterpart will tell us that there is no prompt black hole formation. And we can use this directly to constrain the equation of state, as we have done in the past, and several groups have done similar analysis. If we don't know anything about the mass ratio, then we cannot say things in such a reliable way. We can try to include the mass ratio into our analysis as a sort of systematic uncertainty. And that is essentially what this does, is it broadens the posteriors that we can infer in the analysis. But essentially, these two things are a little bit degenerate. One thing that I want to comment on is that there may be a way, and this is a little bit more speculative, but since it has not been discussed so far, I wanted to bring it up. There may be a way to distinguish these two cases. And the distinguishing factor is in this very fast tail of the ejecta. So if I go back a couple of slides, you see that there is material ejected with very large velocity. And this is really triggered by the shocks formed either at the time of merger, but mostly when the remnant bounces back. And all the binaries that form black holes promptly, even if they are high mass ratio, do not produce fast outflows, because the tidal tail comes out roughly at the escape velocity of the system, which is maybe 0.2 c or so. It doesn't come out at 0.6 c. So the only way to form this very fast ejecta is to have a very violent shock generated when the remnant bounces back. So if we can probe this ejecta, then maybe we can say something more definitive about the formation of the hypermass neutron star. A mechanism has been proposed by Piran and Nakar many years ago, about 10 years ago, I think now, by which we could, in principle, probe this fast tail of the ejecta. So the idea is that this fast tail of the ejecta may interact with the interstellar medium and produce synchrotron radiation, which we could see on months or years time scale from the merger. And this is so-called Kironova afterglow. So this is basically another plot summarizing the same dynamics. This is another binary for which we show central density and fast ejecta. And this is a collection of velocity distribution for many of these binaries. And what we can see is that the trend is always the same. So binaries that form black holes rapidly, even if they are high mass ratio, like this one, mass ratio 1.8, they may form a lot of ejecta, but they will not form a fast velocity component of the ejecta. Binaries that instead bounce back have a very fast state of the ejecta. Curiously, and again, not maybe as anticipated, most of this ejecta is close to the orbital plane. It's not in the direction of the jet. And this is because this is not ejecta coming from the collisional interface between the stars, but it's really coming out of the bounce. So this shock that expands in the debris cloud preferentially accelerates material close to the orbital plane to very large velocities. So recently with a student in Jena, Sevol Nedora, we have done a careful analysis. So he wrote a code to estimate the synchrotron emission from this simulation. So basically taking the output from these simulations, evolving them with semi-analytical equations and computing Kironova afterglow light course, and we find some interesting results. So one of the things that has been exciting for me in the past few months is that there is a very tentative, but in principle possible detection of something that looks like an afterglow. And the observation that you can see here from two different teams of observers, but plotting the same data, is that if we compare the current X-ray luminosity in 17017 to what we would expect from the jet alone, then we find an excess. The emission in 17017 is not rebrightening. It's not like we are seeing something necessarily coming bright again, but we are seeing something that is above the expectations. And interesting, if we plot one of our simulation results without having really many parameters to tune, we find something that in principle would fit the data. And actually, the time scale over which this light course peak in the radio or X-ray is really independent of any fitting parameters. This is really set by simulation properties, so it comes out naturally from the simulation, and the density of the ISM, which is in principle independently constrained from the early afterglow of the GRB.
David, should be close, getting close.
Can you still hear me?
Yes, it's just you have a few minutes left.
Oh, okay. Yeah, I'm basically almost done. So this is a collection of light cores that we find. Essentially, the bottom line is our models cannot really constrain the amplitude of the flux. This depends on microphysics, the shock that is not very well understood. But the output from the simulations predict the time behavior, so up to a scaling up and down of this course. The time at which this course are peaked is essentially not a free parameter in our model. So it's curious that we can feed this data, and it's principally exciting. I think I will conclude. One of the other things that we looked at very recently is with a student here at Penn State, Aviral Prakash. We have been looking at signatures of phase transition in mergers. And one of the interesting aspects, apart from the gravitational wave signal, is that the phase transition results in more violent bounce of the remnant. And so with a more violent bounce, we find a much larger amount of fast-moving ejecta. And so systematically, we see that equations of state that have phase transition or other physics that cause softening in the equation of state at high density, for example, the appearance of hyperons, naturally generate much larger amount of fast-moving ejecta, and so much brighter Kironova afterglow signals. And with that, I conclude. Essentially, what I want to emphasize is the merger dynamics plays a very important role in the EM counterpart. And this is what we can use now to do multi-messenger parameter estimation, because the measure dynamics is understood. And so when we try to constrain the equation of state using EM observation, what we are really doing is we are ruling out models for which we know that all the matter falls inside of the black hole. And so independently of our ignorance of what happens afterwards, we know that the black hole doesn't emit any electromagnetic radiation. If we wanted to do better, we would need models of the long-term evolution of these systems. And this is what we are all working towards. There is some exciting possibility to see the kilonova afterglow. If this signal that we are observing now is the kilonova afterglow, this would tell us that indeed the 17017 formed the hypermassive neutron star that bounced back at least once. I think it's too early now to say for sure what we are seeing, if what we are seeing is the kilonova afterglow, but we'll know for sure in a few years, depending on how the system continues to evolve.
That's great. Thank you, David. It's such a wonderful talk. I think, well, let's first of all thank him and clap. And then I see a lot of raised hands here. Let's see if we can, would ask everyone to be as fast as possible to ask this question so we can take as many as possible. So the first one was V, I believe, and then I lost count who was coming next. Let's go. Svi?
Yeah,
Okay.
Thank you. I think that a very nice feature is that from the afterglow itself, from the early afterglow, we have a good handle about the microphysics. And there is no reason that the microphysics will be very different between the late stage of the ejecta interaction with Dice and the and the similarity, and because we more or less know how to control the conditions in the first part, we can have very good handle on from the late light curve that is possible, hopefully emerging now. We can have very good handle on the distribution of mass versus velocity of the ejecta, which will be a fantastic tool.
Yeah, I agree. My understanding is that the issues, the physics, for example, the fraction of accelerated of energy goes into accelerating relativistic electrons may be different because this shock is only trans-relativistic and not highly relativistic. But I'm not an expert of this. So if you think that we can fix the microphysics given the jet afterglow, then this is great because this is what we have done essentially in these plots here. But otherwise, what I can tell for sure is that the time scale at which these signals peak, this is really something that fixes in our models, and we don't have the control on this. So if it happens that this fits the data for many years in the future, then we'll be confident that this is indeed afterglow.
Okay, so I lost the count. I lost who was first. So I'll go from the first I see there. Brian.
Hi, David. Thanks for the nice talk. Regarding, I'm not going to attack the afterglow model because I was on the paper and I think it's actually a very possible explanation. I do think from the standpoint of arguing the microphysics hasn't changed, the radio is not showing this flattening, so we do need a change in the spectral index of the electrons. And I've also discussed an alternative scenario for producing this is we may be seeing X-rays from the unshielded black hole, which is now accreting fallback at near Eddington. And that could produce X-rays and not radio because we'd be seeing thermal X-rays from the disk. So I agree with you completely. I think it's a little early to say for sure this is the afterglow. We did some recent alpha disk simulations and found there might be enough fallback potentially to explain the level of the X-rays as thermal emission from the remnant. But my question, sorry for the comment, my comment is there may be another explanation if this turns out to be a real flattening of the light curve. And my question is regarding resolution, how confident are we that the kinetic energy of the V greater than 0.6 material is resolved in the simulations?
We have done simulations of 2 or 3 resolutions. And I would say very conservatively that our uncertainty is about a factor 2. And so a factor 2 is not a huge difference in terms of this light course.
Okay, so that's like in kinetic energy above.
There is obviously, here we have a finite number of equations of state. And so the main uncertainty there becomes the equation of state. But if we take the equation of state as a given, then the simulations are not actually doing a bad job at capturing this very fast component of the outflow.
Okay, thank you very much.
Yeah, and thank you for your comment. I didn't have the time to discuss that, but
Yeah.
that's
Okay.
Also compelling.
So there is a time for 2 more quick questions. I'll go in this order. Udi first and then Ben, because Ben is speaking, so he can continue directly to his talk after his question. So Udi, go.
Hi, thanks. Thanks for the talk. I have a short comment, short question or request. As a comment is that the shock breakout is of the jet is probing the fastest 10 to the -7, 10 to the -8, 10 to the -9 solar mass is ejected in the direction of the pole. Now, I know that this is probably impossible to resolve in simulations, but the shock breakout by itself is another probe of the fastest moving material. So this was a comment. And by the way, if indeed 1708-17 was a shock breakout, then there must be a material moving at roughly 0.8 C, 0.8, 0.9. And the second is a question or request. I'm enjoying very, very much reading your papers, one after the other that you're writing on these topics. One thing that I'm a bit missing is a bit more details about the ejecta across the poles. So the jets are basically probing an angle which is roughly similar to the opening angle of the initial opening angle of the jet. So it turns out that even if the cocoon is collimating the jet, the opening angle of the cocoon is similar to the initial opening angle of the jet. So we're talking about, say, 10 degrees, roughly up to 10 degrees around the pole. And there are 2 very critical issues. First, what is the amount of mass going in these directions? Total mass, certainly from the dynamical ejecta, but also if the jet has some delay then from the secular ejecta as well. So what is the total mass, or more conveniently, isotropically equivalent mass in this direction? And the second, what is the distribution over these 10 degrees? Because it's a different propagation if the distribution do not change much over 10 degrees, or if there is a very strong angular dependence also on this small scale, then there can be different issues with the propagation. So I would be happy to know that. I couldn't find it easily in the papers.
Okay, short answer is if you write me after, I can send you all the data. I have, I mean, there is nothing secret in this data. One comment, a short comment I can make is that we can probe the fast moving tail of the ejecta because this is something we can capture in directly in the merger simulation. If you worry about the wind, then there is much more uncertainty there because also our simulations don't have MHD. And so I'm not sure that I would trust the wind over long time scales from these simulations yet, especially high latitude.
Good.
But,
that's great.
Just want the fast moving tail of the ejecta. This is something that I think is reliable already in the simulations, and we can provide the data.
Thanks.
Wonderful. I think I would follow up the suggestion to follow up separately, either on Slack or via email. All right, so Ben, your turn, and then you can go directly to your talk.
That's convenient. Great, thanks. Yeah, David, great, interesting stuff. I guess I was struck by something again. I was on the paper about the 1708-17 rebrightening, so perhaps I should have realized this earlier, but I was struck by your comment about the angular structure, sort of related to what Udi just said, of this bounds component of the fast ejecta, and in particular, how you mentioned that most of it is concentrated near the equator. And I was kind of wondering how that stuff manages to get out of the tidal tails that precede it and that are slower. Does it manage to plow through it?
That's a really a great question. So if you later we can stare at the movie simulations. So what it seems to be happening is that the shock is actually breaking out of the tidal tail. So it's the shock, the tidal tail is forming, the shock is traveling through that material, and then that tip of the material that is what constitutes this very fast moving outflow in these simulations.
Interesting. So it's shock breakout from the tidal tails that is generating this fast outflow?
Yeah, if you see in the simulations, the tidal tail is not really detached from the binary disk time scale, and so it would seem that this is the this is the origin of this fast outflow. That said, we don't have that much data with high time resolution. So to really study this in detail, we need to make a simulation where we do a lot of 3D output, which is expensive, and then look carefully at what is happening in the simulation. But this seems to be intuitively what seems to be happening. Also, because if we look at the angular distribution in phi, there seems to be it seems to be not completely isotropic. So there seems to be some correlation with this forming tidal tails during the merger phase.
Very interesting. Thanks.
Thank you for
All right.
that.